A structure's main function is to transfer loads. But before considering the form of a structure, a clear idea of what loads it has to transfer is required. In other words, an answer to the question what are the loads. The sources of loads can be divided into natural, useful, and accidental loads. Natural loads occur due to the existence of the structure in the world. Useful loads are ones that occur from the purpose of the structure, and accidental loads occur from the misuse of the structure. Firstly, let us talk about natural loads. All structures on the surface of the Earth have to resist the force of gravity. This force acts through a body in a line joining the body with the center of the Earth. However, at the local level these forces can be considered vertical. So the first source of natural loads is the gravity load. For example, the plank across the stream. This means that the plank has to transfer its own weight, usually called self-weight, to the support points. Due to regular and continuous changes in atmospheric pressure, from place to place on the Earth's surface, air flows across the surface of the Earth, that is, wind. All structures built on the Earth's surface have to resist forces from wind. Near to ground level, the wind can be considered to blow along the surface. This is not true for the whole of the atmosphere, as any pilot knows. If an obstruction is placed in the path of the wind, it alters the pattern of the wind flow. This is why kites and planes fly and boats sail. If the object is fixed to the Earth's surface, like a building, the wind must flow around and over it. How the wind flows around and over an object depends both on the wind speed and the shape of the object. These are the basic questions, considered by the complex subject, known as aerodynamics. But the alteration, in wind flow pattern, will always cause a force on the interrupting object. It is an intellectual feat to see the alteration of the wind flow pattern around and over a building as a force or wind load. But this view allows the action of the wind on a building to be clear. So, for the pitched-roofed building, the alteration in wind flow will cause four loads. The loads W1 and W2 are on, and at right angles to the walls, and the loads W3 and W4 are on, and at right angles to the roof slopes. These are wind loads. As far as buildings, and their supporting structures are concerned, gravity and wind loads are two types of natural loads they always have to resist. There are other natural loads that the structure may have to resist. These are earth or water pressure, earthquakes, temperature, and ground movement. If the local shape of the Earth's surface is altered to site the building, as it often is, then parts of the building and its structure may be subject to loads from earth pressure. This is because the natural surface has found a shape that is at rest, not over geological time of course. So, rather like the wind flow, an alteration will cause forces. If dry sand is piled into a heap, there is a maximum slope for the sides. What is happening inside the heap is complex, and is further complicated by the addition of water, which is why sand castles can be made. If, however, a heap with a vertical side is required, forces are needed to keep the heap in the unnatural shape. This is usually done by building a retaining wall. Because the heap wants to return to a natural shape, the wall must hold back all the sand. This causes loads on the wall. In buildings, this occurs when the building has a basement, or is built into a sloping site. In these cases the structure has to resist natural loads from earth pressure. Under the surface of the Earth, depending on the local geology and climate, there will be, at some level, water. The top level of this water is called the water table. This level may be at the surface in swamps, bogs and beaches, or many meters down in deserts. If the siting of the building interrupts the natural water table, an unnatural water table is created around and under the building. Not only are the walls loaded by the water pressure, but it also causes upward loads on the floor. The building is trying to float. The structure has to resist natural loads due to water pressure. The general shape of the surface of the Earth is the same over the lifespan of most buildings, but may alter slightly due to climatic or geological changes. As the building is attached to the surface of the Earth, local changes will force a change in the shape of the structure, as the building is hardly likely to prevent the Earth changing shape. In particular, load may be caused if the local shape changes differentially. It is not obvious how this causes a load on the structure, if indeed it does. For example, suppose the plank bridge has a support in the stream. If this central support were to sink into the stream bed, depending on the fixing, it may pull the plank down, load it, or cease to be a support at all. So ground movements can alter the load-carrying behavior of a structure, and so can be considered, in a rather roundabout way, to load the structure. Another form of ground movement that can load a structure is an earthquake. Earthquakes are caused by sudden internal movements within the Earth's crust. This causes a shock to the system and results in shaking the crust of the Earth over a certain area. The Earth's surface will both bounce up and down and move backwards and forwards. In general, the vertical movement is small compared with the horizontal movement. A building, during an earthquake, undergoes an experience similar to a person standing unaided on a cakewalk. Again, it is not obvious where or what the load is, but the effect, as far as the building is concerned, is the same as being pushed horizontally to and fro with the foundations kept still. So earthquakes cause horizontal loads similar to some extent to wind loads. The last type of natural load is caused by differential dimensional changes in the structure. All structural materials expand when heated and contract when cooled. As structures are often exposed to the ambient climate, their temperature may vary considerably, from a hot summer day to a cold winter night, and in some cases this may cause loads. An example illustrates how this may happen. Suppose a structure consists of two parts firmly joined by a spanning structure. As the temperature varies, the spanning structure will expand and contract. As it is firmly joined to the supporting structures, it will push them and pull them, causing loads. So, as with ground movements, temperature, in a rather unobvious way, may be a load. To avoid these loads, bridges are often provided with systems of sliding bearings at the tops of the supporting columns. On large bridges these can often be seen. A successful structure must be able to resist the effects of some or all of these natural loads for the whole of its useful life. On the whole, these loads cannot be avoided, and are an integral part of the structure's existence. Useful loads. Unlike natural loads, which cannot be avoided and so must be tolerated, useful loads are ones that are welcome. These loads happen because the building and hence the structure have been constructed for a useful purpose. With the plank bridge, it has been constructed for people to cross the stream. If it couldn't do this, it would be of no use. The amount of useful load can be altered by how many people are allowed on the bridge at any one time, and whether people are allowed to take their pet elephants on the bridge. It is often practical for the useful load to be the maximum load that is likely to occur. Practically, the useful load would be a bridge full of people, but no elephants allowed. So, unlike natural loads, there is a choice for useful loads. Of course, if everyone using the bridge had an elephant or a car, it would be sensible for the useful load to be a bridge full of people or full of elephants. As gravity acts on the people and the elephants, the effect of this useful load will be towards the center of the Earth, or locally vertical. Unlike natural loads, useful loads can vary enormously, depending on the use of the building, which may have to carry anything from railway trains to sleeping people. Whilst the majority of useful loads act vertically, sometimes they act horizontally. It may be useful to store sand, grain or water, and these will cause useful earth or water pressure loads. Also, rather like earthquakes, machinery housed in a building may tend to shake a building sideways, causing another type of useful horizontal load. Again, industrial processes may increase or reduce the ambient temperature, giving useful temperature loads. Accidental loads. The occurrence of accidental loads is inextricably bound up with concepts of safety. How safe anything is, driving a car or drinking water, is a matter for society to decide, or at least keep under review. If accidents are thought to be likely, and unavoidable, then the structure should be able to resist loads that these accidents cause. For instance, in a multi-story car park, it is likely and unavoidable that someone will hit the edge barrier whilst parking. The edge barrier should be able to cater for run-of-the-mill collisions but not suicide attempts. Similar situations occur at railway stations and ship berthing jetties. Another unavoidable accident is a minor explosion. Minor explosions in kitchens and bomb factories are of different orders of magnitude, but both should be expected and allowed for. Other unavoidable accidents are crowd panics which require the installation of panic barriers, or tanks bursting which require lower structures to carry the extra liquid load. It is impossible for an individual to decide which accidents, and hence accidental loads, are unavoidable and which aren't, and any society is never clear about this. Compare the number of people killed on the roads in unavoidable accidents and the relatively few killed in train disasters.